Welcome back. We're still here on Monday, May 18th in stats. Now we're going to talk about the binomial distribution, another important and common probability distribution. Here we go. The binomial distribution is meant to describe probabilities for independent yes-no trials. Anytime a random event has only two possible outcomes, called success and failure by statisticians and probability wizards. Probably better to call them yes and no to the question you're asking. But because sometimes, well, we'll see in an example that success is often kind of an inappropriate use of the word. Anyway, only two outcomes, so-called success and so-called failure, both of which have the same probability every time the event occurs. That does not mean they're equally likely. It just means that every time the random event happens, the likelihood of a yes to the question is the same. We'll see lots of examples. And then, well, actually that guarantees that repeated trials of the event have to be independent. No, the probability of a given independent trial, the probability of yes or no never changes from trial to trial. Whenever all that's true, those events are called a Bernoulli trial, named after the Bernoulli brothers, Jakob, and the one who had a less catchy and memorable name, Bernoulli, who are hundreds of years ago mathematicians. The perfect example is flipping a coin. When you grab a coin and you flip it repeatedly, it has the same likelihood of landing heads or tails all the time, as long as you're flipping it with lots of spinning in the air. Other examples that are not 50-50 odds are things like rolling a die. The chance of rolling a 6 on a 6-sided die is always 1 out of 6 if it's a fair die. A non-example, something that's not a Bernoulli card, is when you shuffle up a deck of cards and then you deal them out off the top. As you deal cards, well, the probabilities of getting any of the remaining cards in the deck are changing. So great card players become very well aware of how those probabilities work to become terrific at playing games like bridge and cribbage or gambling. Another example would be like in life, sometimes people are very consistent at things. Portland Trailblazers, I miss you, Portland Trailblazers, I miss you, Damian Lillard. I didn't think about having to think about. I'm not really crying, I was acting. But Portland Trailblazer, Damian Lillard, at least during the season I made this slide, was making fairly consistently 88% of his free throw attempts. I think his career free throw percentage is in the high 80s somewhere still. And really, attempt to attempt, that was a pretty trustworthy likelihood. He's not going to be shaken if he misses one. That's not going to affect his next attempt. And him making one's not going to make him more confident for the next one. This young man has taken thousands upon thousands of free throws throughout his life and practiced to become very, very consistent. Uh-oh, I see in the chat. Thank you, Nick. Thank you for that chat, Oscar, for my acting skills. I really like it. And indeed, Blazers, Jake. Good comments, both. Or if you're just sort of at home rolling your eyes like, who cares about basketball? That's a good silent comment if that's your style too. I actually, when I was young, I grew up in southern Idaho. I never cared about a single professional or college sport. I thought they were all just things that people who liked sports did. And I wasn't a person who likes to do sports. And so I never got into really watching sports. I kind of was creeped out in my hometown. It seemed like people took our football team as seriously as like there'd be fights at football games with kids from the other towns, seemingly because we were at a football game, there'd be like fights. And I thought that was weird. I didn't like that kind of weird townism. So I kind of put me off sports. But then I moved to Portland, Oregon in my early adulthood. I ignored the Blazers for a few years, and then slowly, I noticed they were in the newspaper all the time. And then there was a big labor dispute in the NBA in 1999. I was kind of fascinated by the labor issues. And I started to read the sports page to learn more about what was happening. It was like a battle between billionaires, the team owners, and millionaires, the players, which is a weird battle. But it was interesting to see how a labor battle plays out when everyone is rich. And but as I read about the labor dispute, I learned more and more about the individual players on the Blazers, and then I became a Portland Trail Blazers fan not long after. And today, I do care if Damian Lillard makes those free throws. And yeah, that was not on the slide, but you know. Okay, so now we can describe a random variable. If we think about anytime there's a yes-no trial, so here let's have that be Lillard making free throws. We can think about how many successes he's going to have, how many times he makes a free throw, a success, out of 3 attempts. That number of successes is going to be our random variable, and instead of calling it capital X, like our textbook in the case of a binomial distribution, I'm going to call it capital K. So that's the number of successes, K, out of 3 attempts. And this, I should actually have N equals 3 attempts. So N is going to be the number of random trials, K, the number of successes. And our first goal is to create the probability model for the number of free throws Lillard makes out of 3 attempts, capital K. We're going to list the possible outcomes. We're going to figure out the probabilities. That's 3 free throws, 1, 2, and 3. So we're going to sort them out in a tree diagram. It's going to be the biggest tree diagram we have drawn using the computer so far. And I'm going to do my best to make it on our whiteboard. Here I go. I always make this by hand in class when we're meeting face-to-face because I like doing things at human speed, especially complicated things. Okay, now, so it's make or miss. Let's call that yes or no. So I'm going to do a little K, little notes up here. K is number of made free throws. Can I spell? Kinda. Out of 3 attempts, and that's short for Damian Lillard with an 88%. I'll call it N equals 3 attempts. Likelihood of success. Let's call it a yes. That's made is 88%. And hey, here's your first quiz question. Likelihood no, a missed free throw. What is that? What is the likelihood of Damian Lillard missing his free throw? Just to see if people are awake. Can you chat to me? Thank you, Christina. It's 12%. You can write it. Careful, Janelle. It's 12. Yep, thanks. You got it. I never know if it's a typo or if it's the same kind of arithmetic error that I make sometimes when I'm subtracting numbers from 100. Sometimes I'm off by 10 the first time I do it. So as a mathematician, that happens again and again. And oh, this has notation too. The likelihood of a made free throw is called little p for probability of a make. And the likelihood of a no, well, the math that Christina and Janelle and I all did in our heads, along with those of you who were not chatting about it, is just 1 minus the probability of success p gets you a 12% chance of failure, not making your free throw. And I'm going to put yes and no in a tree diagram. I know it's going to start first free throw, 2 branches, yes and no. So there's going to be 4 branches, yes, no at the second free throw. And the third free throw is going to have yes, no, yes, no, yes, no, yes, no. And since I'm drawing this on this computer, I've learned to draw the last branches first, because then I can actually do some typing over here. So I'm just going to put yes, Y for yes, N for no, Y for yes, N for no, Y for yes, N for no. 1, 2, 3. Can I fit all these on here? Do they all fit? Almost, if I just scooch them up a little bit. Hold on. Wow, okay, so I can fit 8 outcomes. 1, 2, 3, 4, 5, 6, 7, 8. All of those. And then I'm going to have the second free throw would have been here. A yes. Oops, hold on. Let me scoot that up a little bit. Yeah, I'm learning how to draw on computerized whiteboards rather than buy myself a multi-$100 new device to try to draw better pictures for you. Hold on, come on, buddy. You thereabouts. Okay, now this should work pretty well. So yes, no right there. This is the second free throw. There's a yes and a no. Okay, and the first free throw, let me go skinny that up. The first free throw, that would have been back here somewhere. You could have made it, yes, or missed it. See how I'm kind of backwards drawing? Let me draw in all the branches of this tree diagram. So if you made that first free throw, so yes, so here it is, first free throw is that branch, bam, yes or no. Then you could either make or miss your second free throw, yes or no. Whether or not you made or missed the first one, etc. So I'm just sketching in a tree diagram. It takes a few more seconds here in the internet than it does in reality. But you know, as a person who loves tree diagrams, I gotta say I'm learning to love the digital version slowly as I type up more and more of them. And then in every case, in every branch, the likelihoods are easy to write in here. You can see them. They should just, every yes branch should have an 88% for the likelihood of success sort of typed onto it. I'm just gonna write on the branch, and a no, a 12% on every no branch. Let me get the same numbers at every zone here. So an 88% right there, 12% there, 88% success, 12% failure. Maybe I'll make that one. And it's not the most beautiful lining up labeling, but you know, I'm doing the best I can with the tool at hand. So let's just kind of, I think if I just get these ones, 88, 12, heck, I think I can copy and paste this. Copy. And then I can line those up nicely as I like. Oh, hold on. So there's the idea. All of those likelihoods kind of lined up with their paths through the thing. Now, okay, that sorts out every which way this can go. When he takes 3 free throws, you can see yes, 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 made all 3 free throws at the top of the diagram. No, 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 missed them all. And then for every single one of the paths, it's going to tell us the likelihood. Yes, 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 that's the number of makes is 3, right? See that? Now, here's a quiz. What's that number? How do I calculate the number of makes right there, that part of this picture? Well, Christina's got an idea, 88% times 3? 68%. Nicole, how did you calculate that, just so I have a sense of what you're talking about? Oh, yeah. Okay, yeah. Yes. Great. Nick and Christina agree. Nicole just typed it in all at the same time. 88% times 88% times 88%. That is 3 factors of 88%. Okay, right? So I'm just using, that's typing for an exponent. So just 88% times 88% times 88%, 3 factors. Jason's got my style as well. Okay, let's cruise on down the line to here. The probability of no makes. See how that works? No. What are we going to get here? Thank you, Margot's the first in the chat, but there are other folks typing at the same time. 3 factors of 12. Just in this tree diagram encodes the 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 multiplication rule of probability. Multiplying out across these branches gives you conditional probabilities that you can multiply together to get the total likelihood of these events. Now, it gets a little more complicated to get the probability that we're going to get 1 or 2 misses. I want to actually just kind of write it. I'm going to kind of write it like, I'm going to go to this line. So sorry, this line. Just sort of floating here, the probability that you get 2 makes. Okay, now, do you see in that diagram how many paths are there to get 2 makes? Oh, we got this though. This is good. Nicholas has got the path. Along any path with 2 makes, you're going to have 2 factors of 88% and 1 factor of 12%. So I'm going to write that as 88% to the third. Oops, how about like this? Because that's, if I was a math person, I would do that times 12%. I'm using parentheses for multiplication there. Although I think Christina's style, the typing is probably better to read. I'm going to steal your style. Right, so it's 3 factors of 88% times 12%. But do you see now, there's also this question. That'll tell me the probability of getting, oh, sorry, I typed it wrong. It's 2 factors of 88% and 1 factor of 12%. That's this way, yes, yes, no. Or I could go this way, yes, no, yes, correct. Or I could go down here, no, yes, yes. There's 3 ways to do that. How do I take care of that to get the total likelihood of 2 makes? 3 paths through the tree. What do I do with this number that I've got here? This gives me one of those paths. Christina, I like that question. Multiply all of this right here by 3? Yes. So it's 3. That's the number of paths that get me 2 makes times the likelihood of a make, 2 factors of that, times the likelihood of a miss. All right, great. Okay, you are figuring this out pretty well, folks. The likelihood of one make. Right. 1 make, right? So that'd be yes, no, no, or no, yes, no, or yes, or no, no, yes. We're going to have the 2 factors of 12%, right? I'm going to put them in the same order. 1 make and 2 misses, okay? And how many ways, how many paths through? Actually, I like Christina's notation better again. It was three ways to get that, right? 3 ways through the entire graph to get you 2 makes. How many ways can you get 2 misses? Oh, and I typed it wrong. It's 12% to the 2nd power. 3 again. Thank you, Catherine. So 3 ways to get through there. Okay, wow. All right. Whew. So now, and remember, this is a lot of probability thinking, a big tree diagram, a lot of questions, but it's all that basic goal of trying to make a probability density function or a probability distribution function, a PDF. I want to list out the outcomes, and they're right here. 3 makes, 2 makes, 1 make, or 0. And I could list them in descending or ascending order, whatever makes sense. And then I've got the corresponding probabilities written down here. Let me go back to our, oh, this is good. I can go back to our slide, I think. I'm going to go back to our slide. Where are you? There you are. Okay, so the probability model, when we're all done with all that work, what we really want to have is a list of the outcomes, which are called little k, which we had were, I'll put them in ascending order, 0 makes, 1 make, 2 makes, and 3 makes. And we also want to have their corresponding probabilities, right? And let me write let me write out the complicated ones first. There were 3 paths through the tree, and then if we multiplied for 2 makes, we go 88% to the second power times, I like the little x, it's easier to read, 12%. And hey, that 12%, remember the exponent 1 means just the same thing, 1 factor of 12%. I'm just going to write that in there because I'm a math nerd. For 1 make, 3 paths through that big tree diagram, one make gets us 1 factor of 88% times 2 factors of 12% for the 2 misses to get 1 make. Okay, now, the less complicated to calculate values here were the 88% to the third power for 3 makes and 12% to the third power for 3 misses. Now let me just, I'm a math geek, let me just notice for the complicated ones, there was a multiplier for the number of paths through the tree. It was 3 in both cases. I can still do that. 1 path through the tree would get me either of those results, right? There was only 1 way to go. And if you really are a math geek, you would also think, hey, I've got 3 factors of 88%, and I've got 0 factors of 12%. And that's like the exponent 0, okay? Now, are you starting to feel kind of like a math geek a little bit? For 0 makes, that's 0 factors of 88%. Okay. Now, I'm not going to ask you about any patterns for the number of paths through the tree because that's not obvious at all. But is there a completely clear pattern for the number of factors you need for each outcome level for the yes and no likelihoods? Is that pattern totally clear when we write it out like that? Yep, they always have to add up to 3. So for 0 successes, you've got 0 and 3 is 3. 1 success, 1 plus 2 is 3. 2 successes, 2 plus 1 is 3. They always sum to 3. And the number of successes is just right there, the exponent you're applying to the likelihood of success. So this really clear way of just, you don't have to know anything other than how many tries you had and what the likelihood of success is to get that multiplication. These 1, 3, 3, 1, that pattern, that's telling us how many paths through the tree. That is a more complicated pattern to figure out. And it's done using something called the binomial formula. Now, we still haven't calculated these numbers. And of course, we want the numbers. I've never even done the calculations. Now, let me go, let me show you how I would calculate these in not just an example in a math class. I might grab a calculator to type them in. But since I know you're in statistics class and you have access to statistical tools, I'm going to show you how to calculate these very, very quickly using Geogebra. Because we're talking about the binomial distribution because it is a common and important probability distribution. It lives in your Geogebra probability calculator. I don't want to lose my little thing. I'm just going to set it aside. I'm going to set my little note aside and we'll pull it back when I need it. So Geogebra, I'm going into the classic Geogebra. Patiently. You can do it, little laptop. I know you can. I believe in you. Is it my fault? Is it my open windows that are, see my 50 open windows at the top? Is it really all my fault? I don't know. Okay, here we go. GeoGebra's main page, main menu up in the upper right. Sorry. What do I want to see on the home screen? If I want to do some probability calculations using a probability model, I use the probability calculator. There's our normal model friend. We'll go see another friend here. Okay, don't need the menu anymore. Okay, distribution, that means probability distributions. Down here, normal is just an option on a menu. When you hit this menu, you'll see a ton of different options. If you take Stats 2 this summer with your old pal Ralphie, you'll learn about the student distribution, you'll learn about the chi-squared distribution, and you'll learn about the F distribution. If you take further research or research methods courses or statistics courses in your path forward, you could learn about the exponential, Cauchy, Weibull, etc., all those ones. All of them are also smooth curves, so these are all continuous distributions. Then you'll see right there is a line to say, hey, how about some discrete distributions? And the first one on the list is the most common one, the binomial distribution. When you open it up, you'll see a picture that looks like a discrete probability distribution with a set number of outcomes. It's set at 20. So that's, instead of him taking 3 free throws, what if Lillard had taken 20 free throws? The possibilities for his successes would be 0 makes all the way up to 20 makes. Now, the preset for the likelihood is like a coin toss, half and half. You can and we're going to reset both of those to be three shots, and not a half and half likelihood of success, but an 88% chance likelihood of success. And there is the picture of Lillard's work. And looky there are our numbers. That 0017, that is the calculated value. Give me my thing back, you computer. Let me get these into my notes. Clickety clack. That their likelihood of getting a 0 makes is very, very unlikely. He's really good at free throws. The likelihood of 1 make is almost 4%, just a very small value. The likelihood of 2 makes, that's within the realm of possibility, about a 28% chance to the nearest percentage, or a little more accuracy there in the computer. And the most likely outcome, making all 3 free throws, about 68% of the time, even a little more than that. So this is what I expect you to use to do these calculations. When you are asked to make calculations about a situation where there is a set number of yes or no random events, so a set number of yes or no random events where the likelihood of a yes is always the same, and you're asking questions about, well, how many successes or failures out of a certain number of tries, you can always set it up this way and get the calculations done very quickly and very, very accurately. Yeah? Like it? And the trick is to recognize that situation. Let's look back for just a second at the big picture we drew in the whiteboard, because I didn't talk about it enough when I started doing it. I should have said at the very beginning of the long example we went through to figure out how to make these calculations. Here, I'm going to answer your question, Nick. The answer is you never have to make that tree diagram. And I think the analogy is, do you need to open up the hood of your car and look at your engine every day you drive it? No. Do you even have to know how the engine of your car works to drive your car? Yeah, as long as you can see the dashboard, Nick, and that is a perfect, you got to be able to drive safely. So there's things that people need to be able to do to drive, but all you need to do to drive is follow the rules of the road, follow the law, drive safely and respond to, don't hit anybody walking or bicycling or riding a scooter or a pet or a squirrel, just be careful. But there's someone else called a mechanic who works at a garage who will change your oil if you give them money. And they will, fix your broken axle if your axle gets bumped by something on the road and leaks out its axle fluid. I'm just thinking of the last couple things a mechanic fixed on my car because I know nothing about the engine. This is the same kind of a situation. As long as you know what you're going to use the binomial distribution for, and you know you're going to use it correctly, that's like looking at the dashboard. You do not have to look at this. This is the engine of these calculations. What you look at is the dashboard, and that is this. This is your dashboard. So when you're driving a car, you just look at the dashboard. I'm going to go this far. Here's the likelihood of a yes. I'm going to take 3 tries, and I can talk about probabilities. So yes, I do not expect you to ever even think about the formula, which was encoded in that work I did back here on the slide. Or we lost my typing on here, but I had those calculations all typed up. Those calculations depend on a formula that I'm now going to show you. But I want you to remember the formula is part of the engine. The engine is something you don't have to look at unless you want to. I wouldn't tell you to never look at it because there are people, in the car analogy, who like working on their cars. Some of them become mechanics and they do something they like for a living. Some of them just work on their cars to save some money on their oil changes and because it gives them some satisfaction to work on their car. So if you're a person for whom that formula deepens your understanding or helps you get a sense of how this works, you might be a little bit more of a, like some people are more mechanically minded than others, you might be more statistically minded or mathematically minded, and that's good. Go ahead and use that formula as much as you need to develop your understanding. But always check your results using the quick machine, the dashboard GeoGebra. So this slide, oh, Jake, I see your hand. What is on your mind?
So I'm just wondering, with the quiz question, are we able to use that GeoGebra with the binomial line there and input the values?
Yes, 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 yes.
Okay, because I understand when it's only 3, but when the numbers are like 245, obviously you can't draw a tree diagram, so the
Exactly. Yeah.
formula's got to be understood.
Yeah, exactly. So like that's you're like slides ahead of me. So we're gonna yes.
Oh,
No matter
okay.
how many trials there are, the computer's going to be fine getting the calculation done for you. Yeah, people's patience for drawing tree diagrams runs out around 4, 5, maybe 6, 7 random trials for nerds. 7 is a lot of branchings to draw and try to count and think things through. So for most nerds, the picture is just to get a sense of how it works.
Right? Okay, I didn't realize I was ahead much. Are you going to go over the quiz together, how we do that? Because I'm kind of stuck there.
Yes, you bet. We'll get there. Yeah, we'll get there. So all of our discovery of how that works and peeking under the hood in the Lillard example showed us an example of a binomial distribution. Whenever you have a random variable that describes the likelihood, oh, I should underline this. The likelihood of the number of so-called successes out of a number of trials, like that's the only situation where this works. Number of successes, out of a number of trials with set likelihood of success, then you're there. This is the notation for the formula that in parentheses n on top of a k, that's read by mathematicians as n choose k. It tells us how many paths through the tree there are if there are n branchings and you're looking for k successes or k yeses. So how many paths for a chosen number of successes when you have n trials? That's the symbol. And then p, likelihood of success raised to the number of successes, times likelihood of a failure, 1 minus p, and the remaining number of tries left to get you to the total. So this is the formula that captures what we did. Again, if that formula is helpful for you for understanding, go ahead and use it and explore it. If it even just looks confusing, you can forget it exists. Just like I have forgotten what I don't even know what a spark plug is plugged into in a car. I know there's a piece called a spark plug, but I don't know what it's plugged into. A radiator, maybe a transmission. Sorry. But so just trust your gut on exploring the probability. Use the calculator for calculations. Even if you use this, still double check your work with a calculator or a computer. And then the next examples we had were all about, Jake's question foresaw this. As soon as you get a number of attempts that you would not want to draw in a tree diagram, all these questions become questions you can look at over in Geogebra. Now, class time's a little short, so this example might go quickly. I'd recommend, if this is confusing now, go ahead and watch this video, the last video of Monday, May 18th, again, to get a sense of how this works, because I'm not going to take any notes, so I'm going to go a little faster than I would like. Let's take these one at a time. Now we're adjusting the number of attempts to 20 over in Geogebra. That just means, oops, bye-bye. Is this one of the reasons my computer is so slow? I have everything I've ever opened up is still open. Bye-bye. Hello. So number is n, so I'm going to put a 20 right there. Still 88%. And you can see when you drive up the number of attempts, well, the shape of the graph changes. Now, Geogebra will always draw the full range 0 makes, which is pretty much impossible. If Damian Lillard takes 20 free throws, he's not going to miss 20 in a row. So the likelihood rounds away to 0. At 4 decimal places is where they'll start to round away to 0. When you can just kind of see the picture, so like here at 12 or 11, you can see it's above the x-axis. That's where the values don't round away to 0 anymore. And the ones that are really visible even round off to maybe 1%. Now, well, before, making them all was most likely at 3 shots. But if he takes 20 shots, well, actually making 18 is most likely. Because, with 20 tries, when the likelihoods play out, you wouldn't be shocked if he misses 1 or 2 out of 20, or even 3, maybe even 4, if he just has a bad run. So the picture tells a story of how things change. And then we just go back and look at our questions. What's the probability that he makes exactly 13 free throws? Well, when I plugged in the numbers into Geogebra, that got calculated for me right there. 13 free throws. Hey, buddy, come on. Oh, and you can also, you can click through to make an interval. If you're on the interval setting, you can select one value over here, and it'll light up just that number and get you the likelihood, about 0.5% chance of making exactly 13 free throws. Or you can set it up here from 13 to 13 will get you to exactly 13. So you want to make sure, just like in the normal distribution, your drawing matched what you got in the computer. Here, you want to make sure that whatever lights up on the list or in the picture matches what you're really trying to compute. Back here, what is the probability that he makes at most 15 free throws? At most 15, that's 15 or fewer. So I go back to Geogebra. I can go, or fewer is the left-sided thing. I got to make sure it's 15 or fewer. I can type 15 in here, and that should, 15 or fewer. They're all lit up, and they're all added up right there. Wow, it's still a less than 7% chance, or close to 7. No, wait, did I hit that right? Sorry, tired. Hit enter to get things to actually add up correctly when you use Geogebra online especially. It's a little more than an 8% chance of making 15 or fewer free throws. You can see we're basically excluding all of the likely results are excluded, leaving only the rare stuff for a less than 10% chance of that happening. More than 17 free throws. This is the one I actually might take one little note on the screen for this one. So more than 17, let me just do a little math here. More than 7 probability, more than 17. Okay, if I'm symbol wise, that would be x is more than 17. Now here's a quiz. I'll go to more than is down here to the right. It's not a quiz, just double check me here. Is this right? If I type in 17 right there, did I get that right? More than 17. See what's lit up? So it's like always making sure the question being asked matches what we're doing. More than 17, what's the lowest value that is more than 17? 18 and up, yeah, Janelle, thank you. So that more than 17, that's really greater than or equal to, which I type like that, 18, and this does have that or equal to. That doesn't matter in the normal distribution. It totally matters here. So you got to be sure you've got the exact right endpoint. So if you ever have a question about the language in a problem, are you including 18 or not including 18, or are you including 17 or not including 17? Ask the person who asked you the question. And if it's me, I'll make it 100% clear. It doesn't matter if it's on a homework problem, an exam problem. If we were going to mess with this on our project, I would always just make myself clear, because it's not always clear from a phrase like that to every person who reads it if 17 is included or not. So just double check. Next thing. Bye-bye. Calculate the mean and standard deviation of this random variable and explain their meanings. You're going to like this calculation. Check out how challenging it is. There's the mean, okay, mean 17.6. There's the standard deviation, so not a problem at all to find the mean and standard deviation for this probability distribution. So that what that says to us is that this stuff should all balance out weight-wise. Let me slide that way down here. Let me do that. So you can't really see much in the picture now. 17.6, my little mouse is somewhere near the balance point of this histogram now, fairly close. That's 17, maybe and a half-ish, yeah. So somewhere like that is the balance point. And on average, the probability in that picture is a little less than 1.5 distant from that balance point. What that means in context is that if a statistician took this random 20 free throws, that random 20 free throws, that random 20 free throws, that random 20 free throws, and looked at all of his success rates, how many he made in all of those different attempts of 20, then we'd see the long-term expectation of, on average, how many shots you expect Lillard to make out of 20, and what the standard deviation of that expected mean from that expected average, that expected number of makes, should be among many, many sets of 20 free throws attempted. Kind of complicated. The standard deviation is hard to say, but the mean is not. We expect, on average, 17.6 makes out of 20 free throws, long term. Okay, now, where are we? Oh, time is ticking. Let's see how far we've gotten. Okay, then there's another question here about the binomial distribution. Another example. If the probability of a severe lung condition for a smoker is 3/10, what's the distribution of the number of cases of severe lung condition among 4 randomly chosen friends who smoke? find the probabilities using technology. Notice that everything is set up like we need. A set number of people who are being randomly selected, 4 of them, and a set likelihood for developing a severe lung condition, 3/10. All I've got to do is cruise over to my car. I'm going to hop in my car to keep my analogy going. 4 friends, 3/10 is my likelihood, and there's the picture. So among 4 smokers, this is the distribution of the likelihood of 0 of them, 1 of them, 2 of them, 3 of them, or all of them developing a severe lung condition. And you can see 0, 1, and 2 are most common. Okay, peeking on this slide briefly, this gives you a peek. If you use the formula, you can plug in all the values, likelihood of success, likelihood of failure, corresponding number of factors for each one to count how many multipliers you need on each branch, the counting numbers or combination numbers for branchings, 0 successes, 4 branchings, 1 success. And those numbers, there's a cool pattern to them that can be found using a beautiful object called Pascal's triangle. They're called the binomial coefficients, and that's why this is called the binomial distribution. But for us, you'll notice that the numbers that are calculated there, 240, 412, 265, those numbers are right there for us in GeoGebra to 4 decimal accuracy. So we get all of the individual probabilities directly from just setting it up in the computer. And then, you know, they're talking about, hey, you can make the graph, but yeah, we already made the graph. It comes with GeoGebra when you enter in the parameters, number of trials, and likelihood of success. Then there's a couple of slides where they talk about the calculations of expected value and standard deviation, mean and standard deviation. They remind us that they had some fairly complicated formulas. If we're just going to start, if we just wanted to calculate them directly using the outcomes and their probabilities, there's some complicated mathematics to do so. But in the case of these, I'm going to skip this example. Well, in the case of a binomial distribution, there's a straightforward formula for the expected value. It's easy to explain too. Let's look at the smokers. If 4 people smoke and 30% of them are expected to develop a lung condition, on average, out of a group of 4, can you see how that mean got calculated? So I kind of revved up the pace a little bit the last few minutes. Let me slow down with a question. Here's a question. I'm going to type it up. If there are 100 smokers, if there are 100 smokers, random smokers, how many do you expect to develop a severe lung condition? Remembering that the chance of a severe lung condition is this 30% right here. Out of 100 smokers, 30% of them should develop a severe lung condition. How many is that out of 100? 30, okay. Out of 50 smokers. Just kind of changed my question. This one was the answer, yeah, out of, so it'd be 30 out of 100. Out of 50 smokers, we'd expect 15 to develop a severe, not a severe, lung condition. And hold on, that calculation, that was 50 times 30%, right? That was my calculation to get me my 15. Okay, if there are 4 smokers, what do I multiply by 30% to get my expectation here? See that? I'm giving away the game, but see that? If there's 4 smokers, you'd expect 30% of them. So 4 times 30% is 1.2. It's just as straightforward as saying the percentage, view it as a percentage of the number of tries. Long term, that's what you expect for the mean to be among lots of groups of 4 smokers. Standard deviation calculation is a little more complicated. It ends up depending on, the mathematics are just multiply the number of tries by the likelihood of success, by the likelihood of failure, then take the square root. And that quick calculation does the same effect as the complicated standard deviation calculation we learned about for a random variable back in the early part, or the end of chapter 3. Now, I want to get to, there's one last thing here, because we're not quite, skip that for a second. I want to look at I just want to look at our poll question for the day, our attendance quiz, because we're right at the end of class and we have all the tools to do it. We'll talk some more about some of these other issues next class because they're interesting. Okay, this slide is just an introduction. So I'm going to hit it really quickly. 40% of Facebook users in a sample that someone took made a friend request, but 63% received one. So a larger proportion of people get friend requests than make them. Users in the sample pressed the like button, smash that like button, next to friends' content an average of 14 times, but had their own content liked an average of 20 times. So people get more likes than they give on average. Users, on average, sent 9 personal messages, but received 12. Again, getting more than they give. Same thing for tagging photos. 12% of people tagged a friend in a photo, but over a third were themselves tagged. Any guesses how the pattern can be explained? With 0 minutes left in class to talk about it, let me give you the answer. There's people who do more than the average user, like my friend Wayne, who actually quit Facebook because it depressed him too much. Before he quit, he made more comments and posts than almost anybody else I knew. It was great because he's funny and I liked the contact with him, but he would drive up those averages because he was very, very active in social media. It's like that on any social media platform. So power users put in more than most people. Now, here's we made it long ago. Jake was like, asked a question about our attendance quiz. So we're here. Let's go over to our attendance quiz. It's worded a little more simply, and I want to make sure we get it right, because it's kind of an experimental attendance quiz too. I did something I've never done before in the attendance quizzes, and you'll see what it is. Here we go. Binomial distribution attendance quiz. Oh, let me go to just, I'm in student mode. I just click it. Start it up. Okay, here I go. Here we go. A study found that 25% of Facebook users are considered power users. So about 1 in 4 people put in a lot more than they get as Facebook users. The same study found that the average Facebook user has 245 friends. Okay. What is the probability that the average Facebook user who has 245 friends has 70 or more friends who would be considered power users? And there's a hint back on the slide that I want to make sure is here too. That really means 245 friends means there are 245 random little trials. Is that person a power user? Is that person a power user? On down the line. Each of them has a 25% chance of being a power user. And now we're asking, what's the likelihood that we're going to get back a number that is 70 or more, greater than or equal to 70? That's the question. Can you, in the -1 minutes remaining in class, use GeoGebra to answer that question?
Ralph, I input the data. All these answers are coming in. I'm trying to cover the screen so I don't get a spoiler here.
Okay, cool, yeah.
And I input the data, but I'm just confused on how I interpret it. So at the bottom, PK is greater than 70.
That's a great question. Let's get, well, what'd you get for the value? What'd you get for the number?
I put 245 in N, and I put 0.25 for P.
Right on. So that gets you back what number? When you go down into the, Ralphie, when you go to the, sorry, give me my mouse back, computer. When you go, so you've got your 245 right here. Bit, bit, bit. Oh, computer, work with me. Yeah, now we have, it almost looks like a normal curve, and we'll talk about that in next class. So we'll talk more about this next class. 25% right there. Great. 70 or more. So I'm going to go to the right side and hit 70 right there. See that?
I see.
So
Yeah.
my number of trials goes in there, and my probability comes back. And it came back in the chat correctly from Nick, Christina, and Jason. Thank you for your quick typing and response to help your classmates. And now I want all of you to type it into the chat exactly how it looks in GeoGebra. So I want you to just copy and paste that 4-digit number with 0 on the front. Copy and paste that, into your quiz, because it says here, enter your result accurate to 4 decimal places, starting with 0 in the decimal. So it looks just like that. And then hit submit quiz and tell me if that worked. Did that give you a yes, you got it? Hey, all right. I did a quiz with a fill in the blank that worked. I'm so happy. I learned how it works. Great. So don't forget just to enter that in there, that style. If it enters in there and gives you a wrong result, that just means you probably didn't type a 0 or something like that. Because there's a few options for checking it, and I picked regular expression, which means just look at the number and see how it works. So hopefully that works for everybody. Great, thanks for the extra couple of minutes. Sorry for the extra time of your day to get your attendance quiz done, but great work. We made it through enough of that section for you to start that homework. There's a couple of other topics to talk about on Wednesday, and we'll do that. And then we'll get into the next section, which is not as long, but is important. It's about the sampling distribution for sampling proportions. And if we're really lucky, we'll even get into the very beginning of chapter 5 and be close to being in a position to actually discuss all of our topics this quarter, even in this strange online universe. Thank you so much for all your hard work today. I'm going to stop this video because I know folks need to get going to get their lunch for sure. So bye-bye, video viewer. I hope this was helpful for you.